Good afternoon, everyone. Today we're starting systems of linear equations, so let's get into it. So, system of equations is a set of equations that are considered together. In this unit, we'll work with systems of two linear equations. There's possibilities where you could have 3 or 4 or more. A solution to a system of equations is a pair of values that satisfies both equations. So you will have like an x and a y value that both need to be solved for, and when you verify your solution, both equations are satisfied. Okay, so we're going to be focusing a lot today on translating English sentences into math. So we're taking the language of English and translating it into something workable in the math realm. So let's have a read through this, and I think with more examples you'll kind of start to get the hang of this. School district has small buses that carry 12 passengers and large buses that carry 24 passengers. The total passenger capacity for all the buses is 780. There are 20 more small buses than large buses. So it doesn't ask anything in particular yet, but there's small buses and large buses. So I guess something we could do here is just pick a variable. We can maybe call it S, the number of small buses, because there are 20 more small buses than large buses. This sort of seems to be hinting at that we need to find a number for the small buses and the number of the large buses, because that sort of hints toward that. We can let L be the number of large buses. So that's, so far we're just defining our variables. We don't have like more information about the passengers, right? It doesn't say that there's a number more passengers than other passengers, anything like that. So we're getting a lot of information about the buses, so anyways, more examples better. So okay, create a linear system to model this situation. So this is where we need to take the English information and transfer it into math information. So small buses that carry 12 passengers, large buses carry 24. And the total passenger capacity is 780. So, for example, if we had one small bus and one large bus, we would have 12 times 1 plus 24 times 1, and that would give you a number of passengers that we could hold. Right? If we could have, for example, 2 small buses and 1 large bus. That could be a possibility. That would give us another number for the total passenger capacity. So in this situation, we don't know how many small buses and we don't know how many large buses, but we know their combined total has to make 780. So 12 times the number of small buses plus 24 times the number of large buses need to add up to 780. Okay, and then these numbers will adjust. With this equation on its own, we don't know, we won't be able to find how many small and how many large. We can come up with a few possibilities, but nothing will really pin this solution down very likely unless we have more information. And you'll see why in probably a lesson or two. But basically, you need to have the same number of equations in your system as you do variables. So if you have one equation with 2 unknowns, it's basically not solvable. You might be able to make a reasonable guess or several reasonable guesses, but we can't pin this solution down unless we have more information. Anyways, so okay, let's find some more information here. So 20 more small buses than large buses. So the number of large buses plus 20 is the number of small buses. So L plus 20 is S. Okay, you're told that there are 35 small buses and 15 large buses. Use the system to verify. So 35, that's our S. 15, that's our L. So let's check that this first one is correct. So 12 times the number of small buses, so that'd be 35, plus 15 times the number of, sorry, let's go back there, 24 times, geez, lost it all. 12 times 35 plus 24 times 15, that goes in for L. This should work out to 780, but I'm not going to assume that based on the information given. I'm just going to have an open mind and see what this spits out, because I've been told that this works. It should give me that, that's what I expect it to do, but it's not guaranteed at this point. So let's evaluate this. So 12 by 35 is 420, and 24 by 15 is 360. So when we add 420 and 360 together, that gives us 780, which is what we expected. So it works for that one. Now let's check this one. So 20 plus 15 should give us the number of small buses. So the large is 15 plus 20, and this should work out to 35, but let's just check. So 15 and 20, 35, which is right what we would expect. So we're good. Okay, let's look at another example. A school raised $195 by collecting 3,000 items for recycling. They received 5 cents for each pop can and 20 cents for each large bottle. So what unknowns do we want to find? Define variables for those unknown values. So there's, a few things going on here. We see pop cans and we see large bottles. We see, total number of items here, amount of money made. We're kind of looking at the pop can and the large bottle. So if we knew how many pop cans and how many large bottles we had, we'd be able to, connect all these numbers together. So we could just pick a variable. So we could let X be the number of pop cans, and we can get just let maybe Y be the number of large bottles. So this is a critical step in developing a system of linear equations. You need to define variables that you're looking for. If you don't do this step, obviously we're going to have a struggle converting this into a set of equations. So this is a pretty critical step that needs to be done first. So yes, figure out what it is you need to find, define a couple variables. You could call them whatever letter you like, X, Y, QR, PL, whatever you want. Okay, so next we need to create a linear system to model this situation. So $195 by collecting 3,000 items. So we've only collected pop cans and bottles. So the number of pop cans and bottles need to add up to 3,000, right? So if it turned out that I collected 3,000 pop cans, I would have to collect 0 large bottles, right? Maybe if I collected 1,500 pop cans, this one would have to make up the difference, right? So they need to add to 3,000. Okay, and next, $195. So I guess we've got a number of cents here for each of these, and we've got dollars here. So it'd be good to have them all on the same page. We could either work with a number of cents, or we can stay in dollars. So I think I might prefer to work with, so that's dollars, and 5 cents would be $0.05, and 20 cents would be $0.20. So we could do that. Or if you like, you can change this into a number of cents. So $195 equivalent would be, what's it? 19,500 cents. So, I mean, we could do that. It might be actually nicer if we go that way, because then we don't have to deal with decimal numbers. So why don't we go that way? Again, we could do this just as easily in dollars, but I think in this case I'll just choose cents because they're nice clean whole numbers. So that's what we'll do. So suppose we collected one pop can and one large bottle. So if we collected one pop can and one large bottle, how much do we make? 25 cents, right? If we collected, say, maybe, I don't know, 4 pop cans and 2 large bottles, we would have 20 plus 40, so it'd be 60. Okay, so you get the idea, right? We're multiplying the number of small bottles by 5, and we're multiplying the number of large bottles, or sorry, multiplying the number of pop cans by 5, and we're multiplying the number of large bottles by 20, and when we combine those, it gives us the total price. So the number of the number of pop cans is given here, and the number of large bottles is here. So this would be your x, and that's your y. So if we wanted to convert that into a general formula, we'd have 5x plus 20y, and that needs to add up to $195, or because we want to be all in the same units, 19,500 cents. Okay, so super important that the numbers need to be in the same units. Okay, so for example, if I did 5 cents, 20 cents, and 195, so if I used 5, 20, and 195, I would have to collect a lot fewer bottles to make it to 195. So that would be kind of equivalent to me saying each pop can's worth $5, each large bottle is worth $20. How many do I need to reach $195? Well, not that many, right? Okay, so on to the next part. The school collected 2,700 pop cans, so that is our x, and 300 large bottles, so that's y, right? Pop cans, large bottles. Use the system to verify these numbers, so let's check this first equation. So x plus y is 3,000, so we have 2,700 plus 300, and I'm making no assumption about what the total is, but I would expect it to be 3,000. And 2,700 plus 300 is indeed 3,000, so that's what we would expect, so that's good. But we also need to verify that this equation is correct with these numbers. So 5 times 2,700 plus 20 times 300, I would expect this to give that answer. Again, it's not guaranteed, like this is just, you know, we need to get there without making this assumption yet, right? So we're just confirming that this gives us our expectation. Okay, so 5 times 2700 is 13,500, and 20 by 300 is 6,000. So 13,500 plus 6,000 adds up to 19,500. Right, so 6,000 plus 3,000 makes 9,000. We got 500 and 1,000, so 19,500, which is what we'd expect based on our equation. All right, moving on. Store sells wheels for roller skates in packages of 4 and wheels for inline skates in packages of 8. A situation about wheels was modeled by the linear system shown. So I plus r is 80, 8i plus 4r is 440. So inline skates. And we've got roller skates. So it looks like we've got, it would make sense that that would be I, inline skates, and then that's our roller skate. And notice it's 8 by I, so 8 is kind of linked to that number, and 4 is kind of linked to that number. So it looks like we've got some kind of connection there. So I is the packages, or the number of packages of inline skates, and R is packages of roller skates. So next we need to write a problem that is modeled by this linear system. So not usually the way that we'll go with these types of questions. Often we'll be, trying to figure out how to get to these equations, but it is still kind of informative to go the other direction, just to see what we can work with. So 8 times I plus 4r, 440. So it looks like this is the total number of wheels that we're working with here. So if I have a number of packages of inline skates and a number of packages of roller skates, they need to add to 440. And here it looks like the packages need to add to 80. So a possible question could be like, you have 80 packages of stock that arrive. In the form of either roller or inline skates. The total number of wheels in the shipment, 440 wheels total in the shipment. And then we could also add the information that your inline skates come in packages of 8 and your roller skates come in packages of 4, and we can take this information and figure out how many packages of inline skates and how many packages of roller skates. Alright, moving on. Number 4. Hot dog stand sells 3 hot dogs and 5 drinks for $21, 4 drinks and 6 hot dogs for $24. Is the system correct? Okay, so how do we know that? So 3 hot dogs and 5 drinks is $21, and 4 drinks and 6 hot dogs cost $24. So 4 drinks and 6 hot dogs. It looks like, so 3 hot dogs, 3H, and 5 drinks at 21. 4 drinks and 6 hot dogs. So 4, it looks like we've sort of mixed up our things here. So 24 is still correct, but this should change so that it's consistent. We've got 4 drinks plus 6 hot dogs is 24. So that is no good. This one seems fine, right? 3 hot dogs, 5 drinks, as long as it's, we let H be the number of hot dogs and, or the hot dog price rather, and D be the drink price. So there we go. What do the variables represent? H is the price of hot dogs, and D is the price of drinks. Alright, number 5. Determine if the point -10, 1 satisfies or is the solution to either one of the systems shown below. Remember, a solution to a system of 2 equations is a pair of values that satisfy both equations. So it's not enough just to satisfy one of 2. It has to work for both equations in the situation. So looking at this first one, so this would be our x and that would be our y, typically for order of operations, or sorry, an ordered pair. So let's check this first one. So 2 times -10 plus 7 by 1. And I'm expecting it to be -13, but it might not be, so let's just maybe double check. So that'd be -20 plus 7. So -20 plus 7 is indeed -13, so that's what I expect. And I guess we could also, so maybe possibly a better way to set that up is, you know, like this. So does that equal 13? Sorry, -13. I'll try again. So does it equal -13? And yes, it does. So always checking, we're not mixing, right? Keeping all the stuff on the left side, and we're just comparing. So this one is kind of locked in. We're checking that it's consistent, and it is. Okay. So let's check the second system, or the second equation. So -10. So I put -10 in for x plus y, which is 1 again. So I need to check that that is equal to 9. So -10 is +10 plus 1 is that equal to 9? So 11 does not equal 9, so no good. So because the second equation isn't satisfied by this ordered pair, I guess that's the formal way to say it, is no good. Okay, let's try this next one. So x, all right, so make our substitutions again. Everywhere I see an x, I put a -10. So for the first equation, -10, checking this, 3 times 1 minus 13. So -10, 3 minus 13, so 3 minus 13. And 3 minus 13 is indeed -10, so that's good. Now let's check the second one. So 1 goes in for y, -10 goes in for x. We need to check that that equals 21. So this will be 1 plus 20, right? So -2 times -10, or if you prefer 2 times -10 is -20. So if we're subtracting -20, it's the same as adding 20. Okay, 20 plus 1 is obviously 21. So this one works. these equations because they both worked out, right? Both of them were consistent. Okay, sort of the last one here. Is the system of equations defined by these two a system of linear equations? So this one is linear, this one is not, and the reason for that is the exponent here, right? So if you were to graph these in your graphing calculator, coming off of our linear functions unit, negative 3x plus 2, so we'd have something like, that, so that would be a straight line. X squared plus 3, however, would look something like that, which is not linear. So y equals x squared plus 3 is not linear. So therefore, it's not a system of linear. So therefore, not a system of linear equations. Okay, in summary, a system of linear equations contains linear equations. Each equation in the system must be unique, and a solution to the system of linear equations must satisfy all equations. Okay, and we'll get some more practice with making systems out of like word problems, so we'll get more practice with that as we continue, but do make sure that you try some of the practice problems today in your textbook, and at the very least I would like to see that you've completed this. So this is kind of just more work with translating English into math, which is like a very important skill for word problems in this unit. So this is kind of some good things to have in your toolkit. Anyway, that's it for me for today. See you next time.